Hello, trig class. Today is November what? Let me look. Today is Wednesday, November the 4th. So you'll be watching this on the 4th. Let me write that in, 11/4/15. And it's been a while since we've been together like this, so if you don't have your comp book, take notes on a piece of paper and we'll get that into your comp book. So here I am to guide your study ever upward to make you more an amazing person than you already are. So with this inspiration, let's begin learning how to solve trig functions, trig equations. The word equations hints of an equals sign. So we're expecting great things from our equals signs today. So we're going to, the command is not simplify, the command is not verify, the command is solve. And we are going to be solving trig equations like this one, and I'll go through 3 of them and call it a night. Alright, so remember to take notes. Show me your notes tomorrow. My equals sign went a little crazy. Alright, sine x plus square root of 2 equals negative sine x. When you see the command solve, that means at the very end of our happy story, we're going to have x all by its lonesome on one side of the equals sign equals some expression or number on the other side. So I'm not sure where that's going to end, but that will be the end of our story. On this one, sometimes there are restrictions on where we can look for our x, but on this one we'll say we want all values that make this equation true. So no restrictions. In order to solve for a trig equation, you want to get the expression with x in it by itself. So I see sine x, I need to get that by itself. Let's just do some algebraic manipulation. We can move, if we want sine x by itself, it's on one side and the other, we're going to have to move it one way or another. Let's make it positive. So I'm going to add sine x to both sides of the equation. And at the same time, I'm going to move the expressions without sine x to the other side. So I'm going to subtract square root of 2, subtract square root of 2. So once I move some things one way and some things the other, when we add sine x to sine x, we get 2 sine x. And when we move the square root of 2 to the other side, it becomes negative square root of 2. Sine x is still not by itself, so it has a 2 stuck onto it. So I'm going to remove it. It's held there by the glue of multiplication. So I'm ungluing it with division. So I divide it out of the left side and it appears in the denominator on the right. Alright, so that is the end of our getting sine x by itself. But I don't want to know what sine x is, I want to know what x is. So the first step is to get the trig function with the variable, in this case x, by itself, but then to take it a step further to see what x is. So we pull out, this is saying the sine of some angle equals negative square root of 2 over 2. So we're going to pull out our unit circle, and I know square root of 2 over 2 has something to do with the quarters. Like this spot was square root of 2 over 2 over and square root of 2 over 2 up. But I want, remember sine was the second coordinate, and obviously this one's positive, so it's not going to be the answer. We want the negative one. Over here, you'll recall the second one is also positive. But down here, we went back square root of 2 over 2 and down square root of 2 over 2. So we found an angle, this angle right here, that has a second coordinate of negative square root of 2 over 2, or a sine of square root of 2 over 2. So That value, you recall in radians, is 5/4 pi. So 5/4 pi is the answer there. But remember I said there were no restrictions, so I want to make sure I have all the answers. And it turns out that from here to here is 5/4 pi, but what if I don't stop there and I just keep going? What if I go around again like this? You recall, we used to call those coterminal angles. They have the same starting spot and the same ending spot. So the first one was from here to here, but the second one went around an extra 2 pi radians, which is one circle. So I can find another one if I go 5/4 pi plus 2 pi. And of course I could combine those because 2 is 8/4 plus 5/4 is 13/4 pi. But I'll just leave it like that for a minute to make a point. And is there another one? Well, why stop there? Well, we're having such a good time. Let's go around again. So, could I not take 5/4 pi plus 2 pi and add another circle to it? Isn't that another answer? So up here we had 13/4. So if I add another 8/4, we're up to what, 21/4 pi? And could I not go around again? This party is just starting, etc., etc., etc. So the way mathematicians handle this, instead of writing plus 2 pi for the rest of our lives, we write it like this. We say 5/4 pi plus 2 pi times n. What is n? Well, everyone knows. Anyone walking down the hall or anyone in your household, everyone knows that n means the numbers 1, 2, 3, positive whole numbers. So on the first one up here, we generated a 2 pi. Actually, I guess it actually, yeah. When 2 pi was 1, I guess we want to generate this one as well. So let's start with 0. I did say whole numbers, and 0 is a whole number. All right, so the whole numbers, positive ones plus 0, all the whole numbers, 0 is a whole number. So you can see if I substitute 0 in for n, this term goes away. And I get 5/4 pi, which was my first one. And then if n goes up to 1, then we have 5/4 pi plus 1 of these, and that's this answer. And then when n goes up to 2, we get this answer, and so on. So this indicates to the reader that we are going to get all of those iterations, those revolutions around and around and around 2 pi by this notation. Now, one other point is that mathematicians don't write it that way. They write it like this, 2n pi. So this means the same as this, but this is how they write it. And this sort of sets it in a place where it's more understandable, but it means the same here, and this is the common way to express that idea of going around and around and around and generating an infinite number of answers which are coterminal to this value. All right, now back to our unit circle. You recall that we were looking for a place on our unit circle that had the angle had a sign of negative square root of 2 over 2. Is there another place besides all those coterminal ones? Yes, there is another one, and it's down here, right there, where the value is square root of 2 over 2 across, and then negative square root of 2 over 2 down. So that is another one, and the value of that angle right there is, let's see, 1/4, 2, 3/4, 4/4, 5/4, 6/4, 7/4 pi. So we could do the same thing. So 7/4 pi, and we could spin around indefinitely to n pi. Alright, so if you wrote 2 pi n, I couldn't mark it wrong, but this is the conventional way of writing it. So we have completed our first trig equation. Yay! Alright, so we solved the original equation, sine x plus square root of 2 equals negative sine x. If we were to put in any of these values into that equation for x, we would get a true statement. Alright, so that's the first one. Let's look at our second one. I think I'll turn the paper over, because with the drawings and all, I like to spread out. Alright, feel free to stop that if you need to and get all the juicy morsels down. Alright, let's look at this one. 3 tangent squared x minus 1 equals 0. Alright, where'd it go? 3 tangent squared x minus 1 equals 0. Actually, I'm going to do 3 parts because it uploads much quicker if I keep the parts short. So, and I forgot to time it, so I'm out of practice. I'm going to shut down this part and start part 2. See you there.